Hello, friend. Welcome back. Or perhaps, welcome for the first time. Some mornings you wake to sunlight on your pillow. Warm, golden, ordinary. You don't think about it. Why would you? It's always been there. Every single morning of your life. And every morning before you were born. And every morning before that. For 4.6 billion years, the sun has risen. Steady, patient, unquestioning. But here's the thing, most of us forget, or maybe we never really knew, that light on your skin. It's borrowed, temporary, finite. The sun won't shine forever. It can't. And one day long after we're gone, it will dim, swell, and fade into something we wouldn't recognize. Not with a bang, not with fire raining from the sky, but with a slow, gentle, inevitable goodbye. What if the warmth you feel right now is just one breath in a much longer story? A story that's already halfway over. Before we drift into that story together, I want to say thank you. Thank you for being here, for choosing to spend this quiet time with me. If these gentle journeys bring you comfort, if they help you rest or wonder, or simply be still for a while, you might like to stay a little longer. You can softly tap the like button if this feels right to you. Subscribe if you'd like more of these stories whispered into the night. And ring the bell, not for noise, but so the next quiet evening can find you again whenever you need it. No pressure, just an invitation. Now let's drift. Tonight we're going to talk about the sun. Not the sun you see in children's drawings smiling and cartoonish. Not the sun of myths or prayers, but the real sun. The one that exists in the cold mathematics of physics and the slow burn of hydrogen in the silent countdown that began the moment it was born. We're going to talk about what it is, how it lives, and how one day it will die. We'll walk through its past, its present, and its distant inevitable future. You don't need to understand everything. You don't need to remember the numbers or the names. Just rest. Let the story wash over you. Let curiosity do the listening. Because this isn't a lecture, it's a lullaby, science told softly. The sun is a star. You know that, of course. But do you really know what that means? It's easy to forget when it's so close, so familiar, so tied to our daily rhythms. We call it the sun, as if it's the only one, but it's not. It's one star among hundreds of billions in our galaxy alone. And in the grand cosmic catalog, it has a name, not a poetic one. Just a classification. G-type main sequence star. G2V, if you want to be precise. That might sound cold technical, but there's something beautiful hidden in those letters. The G tells us about its temperature, its color, its size. The 2 tells us it's a little hotter than average for its class. The V tells us it's in the prime of its life. And main sequence. That's the long, stable middle chapter where most stars spend most of their existence, burning hydrogen, glowing steadily, doing exactly what they were born to do. Our sun sits in a kind of cosmic sweet spot, not too big, not too small, not too hot, not too cold. Goldilocks if stars had fairy tales. If it were bigger, it would burn faster, brighter, dying young in a violent supernova. If it were smaller, it would burn slower, cooler, barely giving off enough heat to warm a world. But ours is just right, just bright enough to paint the sky blue, just warm enough to keep water liquid, just stable enough to let life take root, grow, evolve, dream. There's a word for stars like this. Some scientists call them the Goldilocks stars. Others just call them lucky. We call them home. Here's something most people get wrong. They think the sun is burning, like a log in a fireplace, like coal in a furnace. But it's not. There's no flame, no oxygen, no combustion. What's happening inside the sun is something far stranger, far more powerful. It's called nuclear fusion. Deep in the core, under pressures we can barely imagine, and temperatures that would vaporize anything we know. Hydrogen atoms are being crushed together. 4 hydrogen nuclei fuse into 1 helium nucleus. In that process, a tiny amount of mass disappears. And that mass, it becomes energy. Pure energy, according to Einstein's famous equation, E equals mc squared. That little bit of missing mass is what powers the sun. It's what warms your face. It's what makes the flowers grow. It's what kept the dinosaurs alive and the first humans and you. Every photon of light that touches you traveled 93 million miles, born from the destruction of something impossibly small. Energy from nothing. Or rather, energy from everything. Let me take you back. Not to your childhood, not to recorded history. Further. Much further. 4.6 billion years ago, there was no sun, not yet. Just a cloud. A vast, cold, slowly rotating cloud of gas and dust drifting through the darkness of space. Mostly hydrogen, some helium. Traces of heavier elements forged in the deaths of earlier stars. This cloud, this nebula, was unremarkable, one of countless billions scattered through the galaxy. But something happened. Maybe a nearby star exploded, sending shock waves rippling outward. Maybe the cloud just reached a critical density. Whatever the cause, it began to collapse. Gravity pulled it inward, tighter, denser, hotter. As it spun, it flattened into a disk. And at the center of that disk, pressure built. Temperature rose. And when it reached about 10 million degrees Celsius, something miraculous occurred. Hydrogen began to fuse. Light erupted. The sun was born. It didn't start out alone. Around it, in that swirling disk of leftover gas and dust, other things were forming. Tiny grains stuck together. Pebbles became boulders. Boulders became mountains. Mountains became worlds. The planets, the moons, the asteroids, all of it sculpted from the leftovers of the sun's birth. We know this not just from theory, but from evidence. Scientists have found grains of silicon carbide inside meteorites, grains that are older than the sun itself. These are stardust, literal remnants of stars that died before ours was born. When you hold a meteorite, you're holding history. You're holding the raw material of creation. And if you look closely enough, you can still see the fingerprints of the nebula, still smell the chemistry of that ancient cloud. It's humbling, isn't it? To know that everything around you, everything you're made of, was once part of something else. We are recycled star matter. The iron in your blood was forged in a supernova. The calcium in your bones came from a dying star. You are quite literally made of the universe. And the universe is made of stories like this. Long, slow, patient, unfolding over billions of years for the last 6 billion years, the sun has been in what astronomers call the main sequence phase. This is the stable part, the reliable part, the part where fusion happens smoothly, where the outward pressure of energy balances the inward pull of gravity, where nothing dramatic occurs. Just steady burning, day after day, year after year, eon after eon. And it will stay in this phase for about another 5 billion years. 5 billion. That's a number so large it loses meaning. But let me try to give you a sense of scale. If the sun's entire life were compressed into a single human lifetime of 80 years, it would currently be about 40 years old. Middle-aged, not young, not old, just steady. And Earth has been around for almost all of it. We've been bathing in the same sunlight for nearly the sun's entire existence. That's why life happened here. Not because we were special, but because we had time. Time for molecules to find each other. Time for cells to divide. Time for complexity to emerge. Time for fish to crawl onto land. Time for dinosaurs to rise and fall. Time for forests to grow and oceans to shift. Time for you to be born and wonder why. Here's what most people don't realize. The sun is unbelievably stable. Compared to other stars, it barely flickers. Its brightness varies by less than 0.1% over decades. That steadiness is rare. Many stars pulsate. They flare. They dim and brighten unpredictably. If our sun did, that life on Earth would be impossible. Imagine if every few thousand years, the temperature dropped by 20 degrees, or spiked by 30. Oceans would freeze, deserts would flood, ecosystems would collapse. But our sun doesn't do that. It just glows, quietly, steadily, like a nightlight left on in a vast, dark room. And that consistency, that boring, beautiful predictability, is what allowed life to take hold. It's what allowed you to exist. You owe your heartbeat to the fact that a ball of plasma 93 million miles away has been remarkably, almost suspiciously well behaved for billions of years. Think about this. Right now, as you listen, photons are streaming from the sun. They left the surface 8 minutes ago. Before that, they spent tens of thousands, maybe hundreds of thousands of years bouncing around inside the sun, slowly working their way out from the core. A photon born in the center of the sun doesn't just shoot out. It collides, scatters, zigzags. Every collision pushes it in a new direction. It's a random walk through a sea of plasma. And eventually, after an unimaginably long journey through the sun's interior, it breaks free, reaches the surface, and then in just 8 minutes, it crosses 93 million miles of empty space and lands on your eyelid, or a leaf, or the ocean. That photon you see when you squint at the sky on a bright afternoon, it's ancient. It started its journey long before you were born, maybe before your grandparents were born, and now it's here, with you, for just a moment. I wonder if you've ever thought about what it means to see the sun. Really see it, not just glance at it, but consider it. When you look at the sun, you're looking at the past. You're seeing it as it was 8 minutes ago. If the sun suddenly vanished right now, we wouldn't know for 8 minutes. The sky would stay bright, the warmth would linger, and then, all at once, darkness, cold, silence. Of course that won't happen. The sun won't vanish, but it will change, slowly, inevitably. And when it does, everything we know will change with it. The ancient Greeks thought the sun was a god, Helios riding his chariot across the sky. The Egyptians worshipped Ra, the sun deity, who died each night and was reborn each morning. The Aztecs believed the sun needed blood to keep burning. Every culture, every civilization has looked up and felt something sacred. And maybe they were right. Not in the literal sense, but in the sense that the sun is the reason we're here. It's the reason anything is here. Without it, Earth would be a frozen rock drifting through space. No oceans, no air, no forests, no music, no love, no dreams, just stone and ice and silence. The sun is not a god, but it is the closest thing we have to one. It gives without asking. It shines without judgment. It has kept us alive for as long as we've existed, and it will outlive us by billions of years. In 1925, a young astronomer named Cecilia Payne made a discovery that changed everything. She analyzed the light from stars and realized that they were made primarily of hydrogen and helium. This was revolutionary. At the time, most scientists thought stars were made of the same stuff as Earth, just hotter. But Payne showed that wasn't true. Stars were different, simpler, made of the lightest elements in the universe. Her discovery was initially dismissed. Her male colleagues told her she must be wrong, but she wasn't. She was right. And eventually the world caught up. Today we know that the sun is about 73% hydrogen, 25% helium, and 2% everything else. All the carbon, nitrogen, oxygen, iron, gold, everything we consider matter in the everyday sense makes up just a sliver of the sun's mass. It's almost entirely the two simplest elements. And yet, from those two simple ingredients, it creates light, warmth, life. The sun doesn't care about us. It doesn't know we exist. It's not burning for our benefit. It's just following the laws of physics. Gravity pulls inward, fusion pushes outward, balance, that's all. And yet, in that mindless mechanical process, it has created the conditions for something extraordinary: consciousness, thought, wonder. You lying here listening to this, thinking about a star, that's the real miracle. Not that the sun exists, but that it exists in such a way that minds can emerge to contemplate it. We are the universe looking at itself. And right now, you're looking at a star that will one day fade. a star that has already lived half its life, a star that is in cosmic terms unremarkable, just one of billions. And yet, to us, it's everything. So here we are, on a small planet orbiting an average star in an ordinary galaxy in a universe that doesn't care. But for now, the sun shines, and that's enough. For now, there's warmth, there's light, there's time, not infinite time, not eternal time, but enough. Enough for you to be here, enough for this moment, enough to wonder what comes next. And what does come next? Let's find out. Let's step inside the sun and see what's really happening in there beneath the surface in the quiet violence where light is born. There are stars out there that make our sun look like a candle next to a bonfire. Stars so massive they could swallow 1,000 suns. Stars so bright they outshine entire galaxies. And then there are stars so small, so dim, they barely glow at all. Red embers in the cosmic dark burning for trillions of years in patient silence. But our sun, it sits right in the middle. Not the biggest, not the smallest, not the hottest, not the coldest, just perfectly average. And that averageness, that's exactly why we're here. Let's talk about what it means to be a G-type star. In the grand catalog of stellar classification, stars are sorted by temperature and color. O, B, A, F, G, K, M. That's the sequence from hottest to coolest. You can remember it with the old mnemonic, "Oh, be a fine girl, kiss me." Outdated, sure, but it sticks. Our sun is a G-type, specifically G2V. The G means it has a surface temperature of around 500 degrees Celsius. Not the scorching 30,000 degrees of a blue giant. Not the cooler 3,000 degrees of a red dwarf. Right in that sweet spot where hydrogen fuses steadily, where light comes out yellow-white, where planets can orbit at just the right distance to stay warm but not boil. The 2 tells us it's slightly hotter than the average G-type star, and the V that's Roman numeral 5, indicating it's a main sequence star, meaning it's in the stable hydrogen-burning phase of its life. Middle-aged, reliable, doing exactly what it was built to do. Now, why does this matter? Why does being a G-type make such a difference? Let's compare. Imagine our sun was a red dwarf instead. Red dwarfs are the most common stars in the galaxy. Small, cool, incredibly long-lived. Some will burn for 10 trillion years, far longer than the current age of the universe. Sounds great, right? But here's the problem. They're dim. So dim that a planet would have to orbit extremely close to get enough warmth. And when you orbit that close to a red dwarf, you get tidally locked. One side always faces the star. One side always faces away. Eternal day on one hemisphere, eternal night on the other. Extreme temperatures, constant stellar flares. Not exactly ideal for life, as we know it. Scientists are still debating whether life could emerge around a red dwarf, but it's complicated, harsh, unstable in ways we don't fully understand yet. Now, imagine the opposite. Imagine our sun was a blue giant, massive, brilliant, spectacular. Blue giants are the rock stars of the universe. They burn hydrogen so fast, so furiously that they die young. A blue giant might only live for 10 million years. That's a cosmic blink. Not nearly enough time for planets to cool, for atmospheres to stabilize, for single-celled organisms to evolve into anything complex. Life needs time, lots of time. And blue giants don't offer that. They live fast, die young, and leave beautiful corpses called supernovae. Our sun will never do that. It doesn't have the mass, and that's a good thing, because if it did, we wouldn't be here to talk about it. Here's what makes G-type stars so special. They live long enough, about 10 billion years give or take, long enough for rocky planets to form, for water to condense, for chemistry to get interesting, for life to not just appear, but to evolve, diversify, complexify. Earth is 4.5 billion years old. Life appeared relatively quickly, maybe within the first billion years. But it took another 3 billion years for anything more complex than single cells to show up. 3 billion years of patience, of slow mutation, of evolutionary trial and error. If our sun only lived for a few 100 million years, we'd still be algae, or we wouldn't exist at all. G-type stars give life room to breathe, time to experiment, time to fail and try again. And then there's the stability. G-type stars don't fluctuate wildly. They're not prone to massive flares that strip away atmospheres. They don't pulsate like variable stars. They just burn, steady, even, predictable. That steadiness creates what astronomers call the habitable zone, or the Goldilocks zone. It's the region around a star where conditions are just right for liquid water to exist on a planet's surface. Not too hot, not too cold. For our sun, that zone stretches from about 0.95 to 1.37 astronomical units. Earth sits at 1 AU right in the heart of it. Venus is too close. Mars is on the edge, maybe just outside. But Earth hit the jackpot. And it's not just luck, it's physics. It's the size of the sun, the temperature, the brightness, all of it conspiring to create a narrow band of space where life could thrive. Let me tell you about a common misconception. A lot of people think the sun is burning, like fire, like combustion, like something you could extinguish with water. But that's not what's happening. The sun isn't burning in any chemical sense. There's no oxygen, no flame. What's happening is nuclear fusion. And fusion is fundamentally different. In a chemical reaction like burning wood, you're just rearranging atoms, breaking bonds, forming new ones. The atoms themselves don't change, but in fusion the atoms do change. Hydrogen nuclei, which are just single protons, get slammed together with such force that they overcome their natural repulsion and fuse into helium. 4 hydrogen nuclei become 1 helium nucleus. And in that process, a tiny bit of mass vanishes. Not destroyed, just converted, turned into energy as Einstein showed us. That missing mass becomes light, heat, the warmth you feel on your face, the glow you see in the sky. It's all from that tiny invisible transformation happening 93 million miles away. Here's another thing people often get wrong. They think fusion happens everywhere in the sun. It doesn't. Fusion only occurs in the core, the innermost 25% of the sun's radius. That's where the pressure is high enough, where the temperature is extreme enough. Out beyond the core in the radiative zone and the convective zone, there's no fusion, just heat slowly making its way outward. The core is where it all begins. Everything else is just the sun carrying that energy to the surface and releasing it into space. And even in the core, fusion is slow, surprisingly slow. A single proton in the sun's core will wait on average about 9 billion years before it fuses with another proton. 9 billion years. That's why the sun lasts so long. It's not burning through its fuel in a frenzy. It's sipping it, slowly, patiently, atom by atom. In 1920, a British astrophysicist named Arthur Eddington proposed that stars were powered by nuclear fusion. At the time, it was a radical idea. Most scientists thought stars burned chemically, or maybe contracted gravitationally to generate heat. But Eddington did the math. He realized that the only way a star could shine for billions of years was if it was converting mass into energy at the nuclear level. He was right, but he couldn't prove it yet. The physics wasn't fully understood. It would take another 2 decades before Hans Bethe worked out the exact mechanisms of stellar fusion in 1938. Bethe showed that in stars like the Sun, fusion happens through a process called the proton-proton chain. 4 protons in, 1 helium nucleus out, energy released. Simple in concept, staggeringly complex in execution. Bethe won the Nobel Prize for this work, and his equations still hold today. We understand fusion, we can describe it mathematically, we just can't replicate it here on Earth in a controlled, sustainable way. Not yet anyway. The sun does it effortlessly, has been doing it for billions of years, and will keep doing it for billions more. We're still trying to catch up. Let me give you a sense of scale. The sun converts about 600 million tons of hydrogen into helium every single second. 600 million tons every second. And in that process, about 4 million tons of mass disappear, converted into energy. That 4 million tons becomes the light that warms the Earth, the radiation that powers photosynthesis, the ultraviolet that gives you a sunburn if you're not careful. All from mass that simply stops existing as matter and starts existing as energy. It's alchemy, not in the medieval sense, but in the real physical universe doesn't care about your intuition sense. And here's the beautiful part. The sun has been doing this for 4.6 billion years, and it's only used up about half its hydrogen. It still has enough fuel for another 5 billion years, maybe more. We're living in the middle of the story, the sun's story, and it's far from over. There's something else that makes G-type stars remarkable. They're common enough that there are billions of them in our galaxy alone, but they're not so common that they dominate. Only about 7% of stars are G-type. Most stars are red dwarfs, making up about 75% of all stars. But G-types hit this perfect balance, common enough that life has plenty of chances to emerge, rare enough that each one feels special. If every star were a red dwarf, the galaxy would be a dimmer, harsher place. If every star were a blue giant, the galaxy would be ablaze with short-lived fireworks. But the mix we have with G-types playing a key role creates diversity. Different kinds of stars, different kinds of planets, different possibilities. And somewhere in that mix on a planet orbiting a G-type star, you happened. Now, let's talk about what makes a star stable. It's all about balance. Gravity wants to crush the star inward. Fusion pushes outward. As long as those two forces are equal, the star stays the same size. It doesn't collapse. It doesn't explode. It just sits there glowing. This is called hydrostatic equilibrium. And for a G-type star, this balance lasts for about 10 billion years. But it's not a static balance, it's dynamic. If fusion speeds up slightly, the star expands a little, which reduces the core density, which slows fusion back down. If fusion slows, the star contracts, which increases density, which speeds fusion back up. It's a self-regulating system, a thermostat built into the laws of physics. And it works beautifully. Our sun has maintained this balance for billions of years. It will maintain it for billions more, until the hydrogen runs out. And when that happens, well, we'll get to that later. Here's a question for you. Have you ever wondered why the sun is yellow? Or is it? If you look at the sun directly, which you shouldn't, it appears yellow or white. But that's because of Earth's atmosphere. The atmosphere scatters shorter wavelengths of light. The blues and violets, which is why the sky looks blue. The longer wavelengths, the reds and yellows pass through more easily. So, we see the sun as yellow, but in space outside the atmosphere, the sun is white, pure white, a blend of all colors. Because a G-type star emits light across the entire visible spectrum, peaking in the blue-green range, but balanced enough that it looks white overall. The yellow sun is an illusion, a beautiful one, but an illusion nonetheless. The real sun is colorless. Or rather, it's all the colors at once. In the 1940s, astronomers developed the Hertzsprung-Russell diagram, a chart that plots stars by their brightness and temperature. It's one of the most important tools in astrophysics. And on that diagram, our sun sits right on the main sequence in the middle of the pack. Not at the top with the giants, not at the bottom with the dwarfs. Right in the middle. A perfectly average star. And there's something comforting about that, isn't there? We're not special, not cosmically. We're just one more star doing what stars do. But that ordinariness is what makes us perfect for life. If we were special, if we were unusual, we'd probably be unstable, unpredictable, dangerous. But we're not. We're boring, steady, reliable. And life loves reliability. Some scientists estimate there could be as many as 6 billion Earth-like planets in the habitable zones of G-type stars in our galaxy alone. 6 billion. That's not counting other types of stars, just G-types. 6 billion chances for life. 6 billion potential homes. We've only just started looking, and we've already found thousands of exoplanets, some around G-type stars, some in the habitable zone. We haven't found life yet, but the search has barely begun. And the more we look, the more we realize how common the conditions for life might be. Not guaranteed, but possible. And possibility is all you need for the universe to try, over and over, billions of times, until something sticks. So, when you look at the sun, remember this. You're not looking at a unique cosmic marvel. You're looking at a typical middle-aged, medium-sized star, one of billions, unremarkable in almost every way. Except for this. It's ours. And it's perfect. Not because it's special, but because it's just right, just stable enough, just bright enough, just long-lived enough to let us be here, to let us wonder, to let us ask why. And that perhaps is the most remarkable thing of all. Not that the sun is extraordinary, but that something so ordinary could create something so complex, so fragile, so brief, so beautiful. And speaking of creation, let's go further back. Let's trace the sun's origins from the cold darkness of a collapsing cloud to the moment it first ignited when hydrogen met pressure and light was born. Before there was light, there was darkness. Not empty darkness, not the void, but a darkness full of potential, a vast cloud of gas and dust, cold and silent, drifting through the spiral arm of a young galaxy. This cloud was enormous, maybe 100 times the mass of the sun, maybe more. It was made mostly of hydrogen with some helium and tiny traces of heavier elements, carbon, oxygen, iron, the remnants of stars that had lived and died before our solar system ever existed. And for millions of years, this cloud just drifted, slowly rotating, slowly contracting under its own gravity, waiting for something to disturb it, for something to begin. About 4.6 billion years ago, something did. Maybe a nearby star exploded in a supernova, sending shock waves rippling outward through space. Maybe the cloud simply reached a critical density where gravity finally overcame the outward pressure of gas. We're not entirely sure, but whatever the trigger, the cloud began to collapse. Not all at once, not uniformly, but in pockets. Regions where the gas was slightly denser started pulling in more gas. Gravity fed on itself, and as the cloud collapsed, it spun faster. Conservation of angular momentum, like a figure skater pulling in their arms. The cloud flattened into a disk, a swirling, rotating disk of gas and dust. And at the center of that disk, pressure began to build. Temperature began to rise. Matter compressed tighter and tighter. And slowly over the course of maybe 50 million years, something new took shape. A protostar, the infant sun. Now, here's where it gets interesting. A protostar isn't really a star yet, not in the way we think of stars. It's not fusing hydrogen. It's just a hot ball of gas glowing from the heat of gravitational collapse. As matter falls inward, potential energy converts to kinetic energy, which converts to heat. The protostar glows, brighter and brighter, hotter and hotter. But it's not stable. Not yet. It's surrounded by a thick envelope of gas and dust that blocks most of the light. If you could see our sun during this phase, it would look like a dim reddish glow buried inside a dense cloud. Beautiful, chaotic, turbulent. This phase lasted for several million years. And during that time, the protostar continued to pull in more matter, growing, heating, spinning, until finally the core reached a critical threshold, 10 million degrees Celsius. At that temperature, hydrogen nuclei start to move fast enough to overcome their mutual repulsion. They collide, they fuse, And when they do, energy is released. Real energy, nuclear energy. At that moment, the protostar became a star. The sun ignited. Light erupted from the core. And for the first time in 4.6 billion years, the sun began to shine. But the sun didn't start alone. Around it in that spinning disk of leftover gas and dust, other things were happening. Tiny particles collided and stuck together. Dust grains became pebbles. Pebbles became rocks. Rocks became planetesimals. And planetesimals over tens of millions of years became planets. This process is called accretion, and it's messy, violent, chaotic. Planetesimals smashed into each other. Some merged, some shattered. The inner solar system close to the sun was too hot for ice to survive. So the planets that formed there, Mercury, Venus, Earth, Mars, were made of rock and metal, heavy elements that could withstand the heat. Further out beyond what we call the frost line, it was cold enough for ice to condense. Water ice, methane ice, ammonia ice. And because ice was so abundant, the planets that formed there grew enormous. Jupiter, Saturn, Uranus, Neptune. Gas giants built on cores of ice and rock wrapped in thick atmospheres of hydrogen and helium. The solar system took shape. And all of it, every planet, every moon, every asteroid, was sculpted from the leftovers of the sun's birth. We know this story not just from theory, but from evidence. Physical, tangible evidence. In the 1960s, scientists began analyzing meteorites that had fallen to Earth. And inside some of those meteorites, they found something astonishing. Tiny grains of silicon carbide smaller than a speck of dust, with isotopic ratios that didn't match anything in our solar system. These grains were older than the sun. They came from other stars, stars that had died before ours was born. When those stars exploded or shed their outer layers, they released these grains into space. And those grains drifting through the galaxy eventually ended up in the cloud that would become our solar system. They were incorporated into the protoplanetary disk, and eventually some of them ended up in meteorites, which fell to Earth, which were picked up by scientists, who analyzed them and realized they were holding stardust. Literal pieces of stars that died billions of years ago. When you hold a meteorite, you're not just holding a rock, you're holding history. You're holding the raw ingredients of creation, the universe's way of recycling itself. And here's something most people don't realize. The sun we see today is not the same sun that formed 4.6 billion years ago. Not physically. I don't mean it's changed location or composition, though. It has slightly. I mean that the atoms inside the sun are constantly being transformed. Hydrogen into helium, helium sitting in the core, inert, waiting. Over the billions of years the sun has been burning, it's converted about half of its original hydrogen into helium. The core is now much richer in helium than it was at birth, and that changes things. Helium is denser than hydrogen, so as helium accumulates, the core contracts slightly. And as it contracts, it heats up. And as it heats up, fusion speeds up, which means the sun is actually getting brighter over time. Not dramatically, not noticeably in a human lifetime, but over geological time scales, yes. Scientists estimate the sun is about 30% brighter now than it was when it first formed. 30%. That's significant. And it has consequences. We'll get to those later. But for now, just sit with that idea. The sun is not static. It's changing, slowly, imperceptibly, but inevitably. Let me take you back to Earth's early history. When the sun first ignited, Earth didn't exist yet, not as a planet. There was just a swirling disk of debris where Earth would eventually be. Over the next 50 to 100 million years, that debris coalesced. Planetesimals collided, merged, grew, and eventually a planet-sized body took shape. But it wasn't Earth, not yet. It was a molten ball of rock constantly bombarded by asteroids and comets. The surface was an ocean of magma. The atmosphere, if you could call it that, was a toxic mix of carbon dioxide, nitrogen, and water vapor. No oxygen, no life. Just heat and chaos and violence. And then About 4.5 billion years ago, something catastrophic happened. A Mars-sized body, which scientists call Theia, collided with the proto-Earth. The impact was unimaginable. It vaporized Theia. It melted much of Earth's surface, and it threw a massive amount of debris into orbit. That debris over time coalesced into the Moon. The Moon is not just Earth's companion. It's a remnant of a cosmic collision, a scar from our planet's violent birth. But here's the beautiful part. That violence, that chaos, it set the stage for life. The impact redistributed Earth's mass. It gave us a large iron core which generates a magnetic field, which shields us from solar radiation. The Moon's formation gave Earth a stabilizing partner, which keeps our axial tilt steady, which moderates our climate. And the bombardment of comets and asteroids, which continued for hundreds of millions of years, delivered water. Lots of water. Enough to fill the oceans. We don't know exactly when the first oceans formed. Maybe 4.4 billion years ago. Maybe earlier. But once they did, Earth had something special. Liquid water, a stable surface, and a sun that shone steadily overhead. And somewhere in those oceans, in the warm, shallow tidal pools, or around hydrothermal vents on the ocean floor, chemistry got interesting. Molecules started interacting in new ways, self-replicating, storing information, metabolizing energy, and life in its simplest form began. The earliest evidence of life on Earth dates to about 3.8 billion years ago, maybe earlier. We've found stromatolites-layered structures created by ancient bacteria in rocks that old. That means life appeared within the first billion years of Earth's existence, relatively quickly in geological terms. And for the next 3 billion years, it stayed simple. Just single-celled organisms, bacteria, archaea, nothing complex, nothing multicellular, just microscopic life quietly photosynthesizing, respiring, evolving. Why did it take so long for complexity to emerge? That's still a mystery. But one thing is clear. Life needed time, lots of time. Time for oxygen to build up in the atmosphere created by photosynthetic bacteria. Time for eukaryotic cells to evolve cells with nuclei and organelles. Time for the first multicellular organisms to appear about 600 million years ago. Time for the Cambrian explosion, when life suddenly diversified into a stunning array of forms. All of this took billions of years, and it all happened under the steady, unchanging light of the sun. Here's something to consider. The sun has been our constant companion for Earth's entire existence. Every major event in Earth's history happened under the same star. The formation of the oceans, the rise of oxygen, the evolution of the first cells, the colonization of land, the reign of the dinosaurs, the ice ages, the emergence of humans, all of it bathed in sunlight. The sun witnessed it all. Not consciously, of course. Stars don't witness anything. They don't care. They just burn. But there's something poetic about it, isn't there? That the same photons warming your skin today are the same kind of photons that warmed the first fish to crawl onto land, that lit the forests of the Carboniferous, that glinted off the eyes of a Tyrannosaurus, that guided the first humans as they looked up and wondered. Now, let's talk about the sun's stability, because that's really the key to everything. Most stars are not as stable as ours. Many stars are variable stars, meaning their brightness changes over time. Some pulsate, some flare, some dim and brighten unpredictably. If our sun did that, life on Earth would be impossible. Imagine if every 10,000 years the sun dimmed by 10%. Ice ages would come and go at random. Ecosystems would collapse. Complex life couldn't adapt fast enough. Or imagine if the sun flared violently like some red dwarfs do. Intense bursts of radiation. Solar storms that strip away atmospheres. Earth would be sterilized over and over. But our sun doesn't do that. It's remarkably calm. Its brightness varies by less than 0.1% over the course of its 11-year solar cycle. That's nothing. barely a flicker. And that steadiness, that boring, beautiful predictability, is what allowed life to take hold and flourish. The sun's stability is not just a feature, it's the foundation of everything we are. Scientists have studied the sun's stability by looking at other G-type stars. We've observed thousands of them. And what we've found is that most G-type stars are stable. Not all, but most. Some have stronger magnetic activity. Some have more frequent flares. But on average, G-type stars are calm, steady, reliable, and that makes them prime candidates for hosting life. In recent years, astronomers have discovered thousands of exoplanets, planets orbiting other stars. And when they find a planet in the habitable zone of a G-type star, they get excited. Because that's the closest analog to Earth we know. Same kind of star, same kind of distance, same potential for liquid water. We haven't found life yet, but we're looking. And every new discovery brings us closer to answering the question, are we alone? Here's a thought experiment. What if the sun had been slightly different? What if it had been 10% more massive? It would burn hotter, brighter, faster. Its lifespan would be shorter. Maybe 6 or 7 billion years instead of 10. That might not sound like much, but remember, it took Earth 4.5 billion years to produce complex life. If the sun only lived for 7 billion years, we'd be cutting it close. Humans appeared less than 1 million years ago. In cosmic terms, we're brand new. If the sun had a shorter lifespan, there might not have been time for intelligence to evolve. Or, what if the sun had been 10% less massive? It would burn cooler, dimmer. The habitable zone would be closer in. Earth would be too far out, too cold, frozen, lifeless. The margins are tighter than you might think. We're not just lucky to have a G-type star. We're lucky to have this particular G-type star, with this particular mass, this particular brightness, this particular stability. It's a cosmic coincidence, or maybe not. Maybe there are billions of solar systems like ours. Maybe the universe is full of Earth-like planets orbiting sun-like stars, quietly evolving their own versions of life. We don't know yet, but the search continues. I want to leave you with one more thought. The sun has been the center of human consciousness for as long as we've been human. Every ancient culture worshipped it in some form. Ra, Helios, Surya, Inti. The sun god took many names, but the reverence was universal. Because on some level, even without understanding the science, humans knew the truth. The sun gives life. It gives warmth. It gives light. Without it, we are nothing. And even now in our modern age, when we understand fusion and photons and nuclear physics, the sun still holds a kind of sacred place. We still watch sunsets and feel something stir inside us. We still seek out sunny days. We still turn our faces toward the light. Maybe it's instinct. Maybe it's something deeper. Maybe it's the universe recognizing itself. You, a collection of atoms gazing at another collection of atoms and feeling connected, feeling small, feeling grateful. But the sun's story is not over. Right now, as you listen, something extraordinary is happening deep inside it. A quiet violence. A transformation so profound, so powerful that it defies imagination. Let's step inside and see what's really going on in there. Right now, as you breathe, something impossible is happening, 93 million miles away. Deep inside the sun, in a place no human will ever visit, no instrument will ever touch, hydrogen is dying, and in its death, it becomes light, becomes heat, becomes the reason you exist. Every second, 600 million tons of hydrogen vanish, not burned, not consumed, transformed into helium, into energy, into the warmth on your skin and the glow in the sky. This is not fire, this is fusion, and it's happening right now, quietly, violently, endlessly. The core of the sun is a place beyond imagination. The temperature there is 15 million degrees Celsius. To put that in perspective, the surface of the sun is only about 5,500 degrees. The core is nearly 3,000 times hotter. At those temperatures, atoms don't behave like atoms anymore. Electrons are stripped away. What's left are naked nuclei, just protons and neutrons moving at incredible speeds, colliding, bouncing off each other, and occasionally, very occasionally, fusing. The pressure in the core is equally extreme, about 250 billion times the atmospheric pressure at Earth's surface. 250 billion times. If you could somehow survive the heat, the pressure alone would crush you into something smaller than a grain of sand. This is not a place for matter as we know it. This is a place where the rules change, where physics becomes both simpler and stranger. Here's how fusion works. Take 4 hydrogen nuclei. Each one is just a single proton, positively charged. And because like charges repel these protons, naturally push away from each other. Under normal conditions, they'd never touch. But in the sun's core, they're moving so fast, colliding with so much energy, that they overcome that repulsion. They get close enough for the strong nuclear force to take over. And when that happens, they fuse. 4 protons become 2 protons and 2 neutrons bound together in a helium nucleus. But here's the critical part. The helium nucleus weighs slightly less than the 4 protons that went into it. Not much less, about 0.7% less. And that missing mass. It doesn't just disappear, it converts into energy according to Einstein's equation. E equals mc squared, a tiny amount of mass, a huge amount of energy. That's what powers the sun. That's what has powered it for 4.6 billion years. And that's what will keep powering it for another 5 billion. Now, let me clarify something people often misunderstand. Fusion doesn't happen everywhere in the sun. It only happens in the core, the innermost 25% of the sun's radius. Out beyond that, in the radiative zone and the convective zone, there's no fusion. The temperature isn't high enough. The pressure isn't high enough. So what's happening in those outer layers? Heat transport. Energy created in the core slowly works its way outward. In the radiative zone, photons bounce from atom to atom, scattering in random directions. It's a chaotic journey. A photon created in the core might take 100,000 years to reach the surface, maybe 200,000 years. Some estimates go even higher. It zigzags, collides, changes direction millions of times, slowly making its way outward. And then, in the convective zone, closer to the surface, the energy is carried by convection. Hot plasma rises, cools, sinks back down, heats up again, rises. It's like a pot of boiling water, but on a scale that dwarfs anything we can imagine. Let me give you a sense of just how slow fusion is. In the sun's core, a single proton will wait on average about 9 billion years before it fuses with another proton. 9 billion years. That's longer than the current age of the sun, longer than the current age of the universe. And yet, because there are so many protons in the core, trillions upon trillions upon trillions, fusion happens constantly. Every second, about 600 million tons of hydrogen fuse into helium. Every second. And in that process, about 4 million tons of mass are converted into energy. 4 million tons. Every second. For 4.6 billion years. And the sun has barely noticed. It's still got enough hydrogen to keep this going for another 5 billion years. Maybe more. Fusion is slow, but the sun is patient. And it has time. So much time. In the 1930s, a German physicist named Hans Bethe worked out the exact mechanism by which stars like the sun fuse hydrogen into helium. It's called the proton-proton chain. It happens in several steps. First, 2 protons collide and fuse, creating a deuterium nucleus, a positron, and a neutrino. The positron quickly annihilates with an electron, releasing more energy. The deuterium nucleus then collides with another proton, forming helium-3 and releasing a gamma-ray photon. Finally, 2 helium-3 nuclei collide, forming helium-4 and releasing 2 protons back into the mix. It sounds complicated, and it is, but Bethe reduced it to mathematics. He showed that you could predict with extraordinary precision how much energy a star would produce based on its mass and composition. He won the Nobel Prize for this work in 1967, and his equations are still used today. We understand fusion. We can describe it. We just can't replicate it efficiently here on Earth. Not yet. Now let's talk about something strange, something most people never think about. Neutrinos. When hydrogen fuses in the sun's core, it doesn't just produce helium and energy, it also produces neutrinos. Tiny, nearly massless particles that barely interact with anything. A neutrino can pass through a light year of lead without touching a single atom. They're ghosts, phantoms. And the sun produces them in unimaginable quantities. Trillions upon trillions every second. Right now, as you listen, about 65 billion neutrinos from the sun are passing through every square centimeter of your body. Every second. 65 billion. And you don't feel them. They pass through you like you're not even there. They pass through the earth, through the walls of your house, through your bones and organs and skin. And they just keep going. Out into space. Forever. In the 1960s, a scientist named Raymond Davis built a detector deep underground in a gold mine in South Dakota. It was filled with 100,000 gallons of cleaning fluid perchloroethylene. The idea was simple. If a neutrino happened to hit a chlorine atom in the tank, it would convert it into argon. And by measuring the argon, you could count the neutrinos. Davis ran this experiment for decades, and he found neutrinos, proof that fusion was happening in the sun's core. But there was a problem. He found only about a third as many neutrinos as theory predicted. This was called the solar neutrino problem, and it puzzled scientists for years. Were the theories wrong? Was the sun dying? No. It turned out neutrinos were stranger than anyone realized. They come in 3 types or flavors: electron neutrinos, muon neutrinos, tau neutrinos. And as they travel, they oscillate between these flavors. Davis's detector could only detect electron neutrinos. The other 2/3 were there, he just couldn't see them. When scientists finally figured this out, in the late 1990s, it solved the mystery, and it confirmed beyond any doubt that fusion is happening in the sun, right now, as it has been for billions of years. Here's something else to consider. The energy released in fusion doesn't leave the sun immediately. Remember, photons created in the core take hundreds of thousands of years to reach the surface. But neutrinos, they escape instantly, within seconds. Because they barely interact with matter, they just fly straight out. Which means the neutrinos we detect today were created in the sun's core just 8 minutes ago. That's how long it takes light or neutrinos to travel from the sun to Earth. 8 minutes. But the light you see? The photons warming your face. They were created 100,000 years ago. Maybe more. They've been trapped inside the sun, bouncing around slowly, working their way outward for longer than human civilization has existed. And now, finally they're free. And one of them just happened to land on you. Let's talk about the balance that keeps the sun stable. It's a perfect tug-of-war. Gravity wants to crush the sun inward. Fusion pushes outward. As long as these 2 forces are equal, the sun stays the same size. This is called hydrostatic equilibrium. But it's not a static balance, it's dynamic, self-regulating. If fusion speeds up the core, heats up, which causes it to expand slightly, which reduces the density, which slows fusion back down. If fusion slows, the core cools, which causes it to contract, which increases the density, which speeds fusion back up. It's a thermostat, a feedback loop built into the laws of physics, and it works beautifully. For billions of years, the sun has maintained this balance. Gravity and fusion locked in a dance, neither winning, neither losing. Just holding, steady, patient, waiting. But here's the thing. That balance won't last forever. Right now, the sun is fusing hydrogen into helium, and all that helium just sits in the core. Helium doesn't fuse. Not at these temperatures, not at these pressures. So it accumulates, slowly, over billions of years, And as it accumulates, the core gets denser, heavier, and as it gets denser, it contracts slightly. And as it contracts, it heats up. And as it heats up, fusion speeds up, which means the sun is actually getting brighter over time. Not much, not noticeably, but measurably. Scientists estimate the sun is about 30% brighter now than it was when it first formed. In another billion years, it might be 10% brighter than it is today. That has consequences, serious consequences. But we'll get to that later. For now, I want you to think about what it means that the sun is changing, slowly, imperceptibly, but inevitably. We think of the sun as eternal, unchanging, a constant in our lives, but it's not. It's evolving, aging, moving through its life cycle. Right now, it's middle-aged, stable, reliable, but one day it won't be. One day the hydrogen in the core will run out. And when that happens, the balance will break. Gravity will start to win, the core will contract, the outer layers will expand, and the sun will transform into something we wouldn't recognize. A red giant, swollen, dying, beautiful in a way, terrifying in another. But we're not there yet, not even close. Right now, the sun is doing exactly what it's supposed to do, fusing hydrogen, releasing energy, shining steadily. And that steadiness, that boring, beautiful predictability, is what allows you to be here, listening, breathing, existing. You are the product of 4.6 billion years of stellar stability. Every atom in your body was forged in a star. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it came from stars that lived and died before the sun was born. And now, here you are. A temporary arrangement of stardust, warmed by another star, thinking about where it all came from, thinking about where it's all going. Have you ever wondered what it would be like to see the sun's core? To witness fusion firsthand, you can, of course. The core is hidden. Buried beneath 432,000 miles of plasma, unreachable, unknowable except through mathematics and indirect observation. But in a way, you do see it. Every time you look at the sun, you're seeing the result of fusion, the light, the heat, the energy that traveled so far for so long just to reach you. That's the core's gift, its legacy. And it's given freely, without asking for anything in return. Just burning, shining, existing, and it will keep burning for a long time yet. Longer than you, longer than humanity, longer than any civilization we can imagine, but not forever. Nothing lasts forever, not even stars. And when the sun's time comes, when the hydrogen finally runs out, it will begin the long, slow process of dying. But before it dies, it will swell, it will expand, it will reach out across the solar system, consuming everything in its path. And that transformation, that final act, will be both terrible and beautiful. Let's see what that looks like. Imagine waking up one morning and the sun has doubled in size. The sky glows a deep, angry red. The heat is unbearable. Oceans boil, continents crack, and you realize with absolute certainty that this is the end. Not just the end of you, the end of everything. The sun is dying. And in its death, it's taken the entire inner solar system with it. This won't happen tomorrow, not in 1,000 years, not even in 1,000,000. But in about 5 billion years, give or take, this will be our sun's reality. It will swell, it will redden, and it will consume the worlds closest to it. Mercury, Venus, possibly Earth. This is the red giant phase, and it's as inevitable as sunrise. Here's what triggers it. Right now, the sun is fusing hydrogen in its core. That fusion creates an outward pressure that balances gravity's inward pull. Equilibrium, stability. But hydrogen doesn't last forever. Over billions of years, the core converts more and more hydrogen into helium. And helium at the temperatures and pressures in the current core doesn't fuse. It just sits there, accumulating, waiting. Eventually, about 5 billion years from now, the hydrogen in the core will run out, completely. And when that happens, fusion stops. The outward pressure vanishes, and gravity, which has been waiting patiently for billions of years, finally wins. The core begins to collapse, not explosively, not violently, just slowly, quietly, contracting under its own weight. And as it contracts, it heats up. The temperature rises, the pressure builds, and something strange happens. Hydrogen in a shell around the inert helium core starts fusing. Shell burning, scientists call it. And this shell produces even more energy than core fusion ever did. That extra energy has nowhere to go but outward. It pushes against the sun's outer layers, forcing them to expand. And expand. And expand. Over the course of a few 100 million years, the sun will grow to 250 times its current size, maybe more. Its diameter will stretch beyond the orbit of Mercury, past Venus, possibly reaching Earth's orbit. The sun will become a red giant. Its surface temperature will drop to about 3,000 degrees Celsius, much cooler than the 5,500 degrees it is now. And because cooler objects emit redder light, the sun will glow a deep crimson red. If you could stand on a planet far enough away to survive, you'd see a massive bloated star filling half the sky. Beautiful, terrifying, unrecognizable. Now, here's where it gets complicated. Scientists aren't entirely sure what will happen to Earth. The sun will definitely engulf Mercury. Mercury is too close. It has no chance. Venus, too, will almost certainly be swallowed. But Earth is right on the edge. Some models suggest the sun's outer layers will reach Earth's orbit and consume it. Others suggest Earth might survive. Why the uncertainty? Because as the sun expands, it will lose mass. Solar wind will strip away its outer layers. And as the sun loses mass, its gravitational pull weakens, which means the planet's orbits will shift outward. Earth might drift far enough away to escape, or it might not. The calculations are close, too close to call with certainty. But even if Earth survives being swallowed, it won't survive intact. The heat will be unbearable. Oceans will evaporate. The atmosphere will be stripped away. The surface will melt. Earth will become a charred, lifeless rock, drifting through space, forever locked in orbit around a dying star. Let me give you a sense of scale. Right now, the sun's radius is about 432,000 miles. When it becomes a red giant, its radius could reach 100 million miles or more. That's the distance from the sun to Earth. The entire space between the sun and Earth, filled with the sun's outer atmosphere. Imagine that. Standing on Earth, looking up and seeing nothing but the sun. No stars, no moon. Just a vast red glow that stretches from horizon to horizon, filling the entire sky. And the heat. Oh, the heat. Even before the sun reaches Earth, the temperature will rise enough to boil the oceans. Scientists estimate that within 1 billion years, maybe less Earth's surface temperature will exceed the boiling point of water. Life, as we know it, will end long before the sun swallows us. Long before the red giant phase even begins. We'll be gone, one way or another. Here's something most people don't realize. The sun won't just expand once and stay that way, it will pulsate. During the red giant phase, the outer layers will expand and contract rhythmically. Every few 100,000 years, the sun will swell larger, then shrink back down, then swell again. These pulsations are driven by instabilities in the shell-burning process. Sometimes fusion speeds up. Sometimes it slows down. And each time it changes, the sun's size changes with it. Astronomers have observed this in other red giants, stars like Mira in the constellation Cetus. Mira pulsates with a period of about 332 days. It swells to 400 times the size of the sun, then contracts, then swells again. Regular, predictable, inevitable. Our sun will do the same, not as dramatically, not as quickly, but the pattern will be there. A slow, cosmic heartbeat. The dying breaths of a star. Now, let's talk about what happens inside the sun during this phase. Remember, the core is still collapsing, still heating up, and eventually it reaches a critical temperature, about 100 million degrees Celsius. At that temperature, helium starts to fuse, not gradually, not gently, but suddenly, explosively. This event is called the helium flash. In a matter of seconds, the core releases as much energy as the entire galaxy. But because the core is so dense, so deeply buried, none of that energy escapes. It's absorbed by the surrounding layers. The core stabilizes. And for a brief period, maybe 100 million years, the sun burns helium in its core. Helium fuses into carbon. Carbon fuses into oxygen. The core becomes a mix of carbon and oxygen, inert once again. And then the cycle repeats. Helium shell burning, more expansion, more pulsations. The sun is in its death throes, and it's running out of options. Let me tell you about a star we've studied closely. Betelgeuse. It's a red supergiant in the constellation Orion, much more massive than our sun, but it's going through a similar process. Betelgeuse has already left the main sequence. It's fusing heavier elements in its core, and it's enormous. If you place Betelgeuse where our sun is, it would extend past the orbit of Mars, maybe even Jupiter. It's so large that we can actually see its surface with telescopes, not as a point of light, but as a disk, a mottled turbulent surface with convection cells the size of Earth's orbit. Betelgeuse is unstable. Its brightness varies. Sometimes it dims dramatically. In 2019 and 2020, it dimmed by about 40%, sparking speculation that it might go supernova. It didn't, but it will. Someday. Maybe tomorrow. Maybe in 100,000 years. We don't know. But when it does, it will be visible in daylight. A new star blazing in the sky, brighter than the full moon. Our sun won't do that. It's not massive enough. But Betelgeuse shows us what dying stars look like. Chaotic, unstable, magnificent. Here's a thought that might keep you up at night. The red giant phase is not unique to our sun. It's the fate of every star with a mass between about 0.5 and 8 solar masses. That's most stars, billions and billions of them. Right now, all across the galaxy, stars are swelling into red giants, consuming their planets, dying slowly. And billions of years from now, long after our sun has faded, other stars will do the same. The galaxy is full of endings, full of quiet deaths, full of stars that once shone brightly, that once warmed worlds, that once made life possible, now bloated and red and fading. It's a reminder that nothing lasts, not even stars, not even the things that seem eternal. But here's the beautiful part. The red giant phase, as destructive as it is also creative. As the sun loses mass, as its outer layers drift away into space, they carry with them the elements forged in its core. Carbon, nitrogen, oxygen, the building blocks of life. These elements will spread through the galaxy. They'll mix with clouds of gas and dust. And eventually they'll become part of new stars, new planets, maybe even new life. The sun's death will seed the cosmos. It will give back what it took. And in that sense, the red giant phase is not an ending. It's a transformation, a passing of the torch, the universe recycling itself as it always has, as it always will. Scientists have studied the red giant phase extensively, not just through theory, but through observation. We've cataloged thousands of red giants. Some are nearby. Arcturus in the constellation Boötes is a red giant about 37 light-years away. Aldebaran, the Eye of Taurus, is another. These stars give us a glimpse of our sun's future. They're cooler, redder, larger, and they're losing mass. Stellar wind, a stream of particles flowing away from the star, carries away about 1/10,000,000th of the star's mass every year. That doesn't sound like much, but over 100 million years, it adds up. By the time the sun finishes its red giant phase, it will have lost about 30% of its mass, maybe more, all of it blown away into space. A slow, gentle unraveling. Here's something people often get wrong. They think the sun will explode, like a supernova, a massive catastrophic blast that destroys everything. But that's not what happens. The sun doesn't have enough mass for a supernova. Only stars at least 8 times more massive than the sun can do that. Our sun will die quietly, gently. It will puff off its outer layers. It will shrink down to a hot, dense core. And it will fade. No explosion, no fireworks, just a slow dimming. A quiet exit. In a way that's more poignant, isn't it? Not a violent end, but a gentle one. A star that gave life for billions of years finally letting go, releasing its hold, drifting into silence. But before that silence comes, there's one more act. One more transformation. As the sun sheds its outer layers, as the red giant phase ends, something extraordinary happens. Those outer layers drifting away from the core begin to glow, illuminated by the ultraviolet radiation from the hot core beneath. They form a shell, a glowing, expanding shell of gas, and from a distance it looks like a ring, or a bubble, or a flower, delicate, symmetrical, beautiful. This is called a planetary nebula, and it's one of the most stunning sights in the universe. But we'll explore that in a moment. For now, just know this: the sun's death will not be ugly. It will be art. There are things in space so beautiful they don't look real. Structures so delicate, so symmetrical, they seem painted rather than formed by physics. Rings of glowing gas, shells of light expanding through the darkness, colors you've never seen together. Blue and green and violet and red, all swirling in patterns that look almost intentional, almost artistic. These are planetary nebulae. And despite the name, they have nothing to do with planets. They're the ghosts of dying stars, the final fleeting exhale before silence. And one day, billions of years from now, the sun will create one, a last work of art, a monument to everything it was. The name is misleading. In the 1780s, the astronomer William Herschel looked through his telescope and saw these fuzzy round objects scattered across the sky. Through the crude optics of the time, they looked somewhat like planets, greenish, disc-shaped. He didn't know what they were, so he called them planetary nebulae. The name stuck, even after we realized they had nothing to do with planets at all. They're not even permanent structures. They fade, they dissipate. Within 10,000 to 20,000 years, they vanish completely, their gas spreading too thin to see. But while they last, they're among the most spectacular objects in the universe. Fragile, transient, beautiful precisely because they don't last. Here's how they form. After the red giant phase, after the sun has swelled and pulsated and lost much of its outer layers, what's left is a hot, dense core surrounded by a thin shell of gas. The core now exposed is incredibly hot, over 100,000 degrees Celsius. And it's radiating intense ultraviolet light. That ultraviolet light strikes the surrounding gas, ionizing it, making it glow. The gas still drifting outward from when the star shed its layers forms a shell, and that shell, illuminated from within, becomes a planetary nebula. It's like turning on a light inside a paper lantern. The structure was always there, but now it glows. Now it's visible. Now it's art. The shapes are astonishing. Some planetary nebulae are perfect spheres. Others are rings. Some look like hourglasses or butterflies. Others are chaotic with jets and knots and filaments shooting out in all directions. Why the variety scientists aren't entirely sure. It probably has to do with the star's rotation, its magnetic field, maybe the presence of a companion star. If a star is spinning, its stellar wind might be stronger at the equator than at the poles, creating a flattened shape. If there's a companion star, its gravity might sculpt the outflowing gas into lobes or spirals. Every planetary nebula is unique, a fingerprint, a portrait of a star's final moments written in light and gas. Let me tell you about a few famous ones. The Ring Nebula in the constellation Lyra. It's about 2,000 light-years away. Through a small telescope, it looks like a pale, glowing donut. A ring of gas surrounding a tiny, faint star. That star is the remnant core. a white dwarf, and the ring is the outer layers still glowing, still expanding, slowly fading into the dark. The Helix Nebula in Aquarius is closer, about 700 light-years away. It's often called the Eye of God because it looks like a giant eye staring back at us. A circular nebula with intricate structure, threads and knots of gas, each one bigger than the distance from the Sun to Pluto. And at the center, a white dwarf, cooling, dimming, fading. The Cat's Eye Nebula in Draco is one of the most complex. Multiple shells, concentric rings, jets of gas shooting out from the poles. It looks like something alive, something breathing, but it's not. It's just physics, just the remnants of a star expanding into space, glowing for a brief cosmic moment before vanishing forever. Here's something that surprises people. Planetary nebulae are rich in heavy elements: carbon, nitrogen, oxygen. These are the elements forged in the star's core during its final stages of fusion. When the star sheds its outer layers, these elements go with it. They spread through space. They mix with clouds of gas and dust. And eventually, they become part of new stars, new planets, new life. Every atom of carbon in your body was created inside a star, not our sun, an earlier star. A star that died billions of years ago that created a planetary nebula that seeded the galaxy with the raw materials for life. You are made of stardust, literally. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it came from stars like this. Stars that died so you could exist. Now, let's talk about the timeline. A planetary nebula doesn't last long. In cosmic terms, it's a blink. The gas expands at speeds of about 20 to 30 kilometers per second. Fast, but not relativistic. Not close to the speed of light. Over thousands of years, the shell grows larger and larger, fainter and fainter. The ultraviolet light from the central white dwarf starts to dim as the dwarf cools, and eventually the gas becomes too diffuse to glow. It fades into invisibility. After about 20,000 years, most planetary nebulae are gone, not destroyed, just spread too thin to see. The atoms are still there, drifting, waiting, ready to be incorporated into the next generation of stars. In 1968, a group of astronomers discovered something strange. They found a planetary nebula around a star called NGC 6302, also known as the Bug Nebula or the Butterfly Nebula. It's in the constellation Scorpius, about 4,000 light-years away. The nebula is enormous. The gas extends for more than 2 light-years in each direction. And it's moving incredibly fast. Some parts are traveling at 600 kilometers per second. That's far faster than typical planetary nebulae. Scientists think this might be due to a binary companion star, something hidden in the glare, gravitationally flinging material outward. The structure is bizarre. 2 lobes like wings with a dense disk of dust in the middle. The central star is hidden. We can't see it directly, but we know it's there because the nebula is glowing, powered by something unseen. Here's a common misconception. People think planetary nebulae are explosions, like supernovae, violent, catastrophic, but they're not. They're gentle. The star doesn't explode. It just sheds, layer by layer, slowly, patiently, like peeling an onion. Each layer drifts away at its own pace, creating shells within shells. Some planetary nebulae have multiple rings, each one representing a different episode of mass loss. The star pulsates, ejects material, rests, pulsates again, ejects more. Over hundreds of thousands of years, this process creates intricate structures, nested shells, concentric halos, beauty through repetition, through patience, through the slow unwinding of a star's outer envelope. Now imagine what this would look like from Earth. Billions of years from now, long after humanity is gone, the sun will have entered its red giant phase. It will have swelled, pulsated, shed its outer layers. And then As those layers drift away, they'll start to glow. The sun's core now, a white dwarf, will illuminate them with ultraviolet light. And if there were anyone left to see it, if there were observers on some distant world, they would see a planetary nebula where the sun used to be. A glowing ring of gas expanding into space, colors shifting as different elements emit different wavelengths of light. Red from hydrogen, green from oxygen, blue from helium. A cosmic aurora, a final burst of beauty before the long silence. But here's the thing, we won't be there to see it. Humanity, if we still exist by then, will have left the solar system long ago. We'll have no choice. The sun's transformation will destroy Earth or render it uninhabitable billions of years before the planetary nebula forms. So, the sun's final act, its most beautiful moment, will happen in an empty solar system. No witnesses, no applause, just light and gas glowing briefly then fading. It's poignant, isn't it? That the universe creates such beauty not for anyone, but just because that's what physics does. It doesn't care if anyone sees, it just creates. And then it lets go. Scientists estimate there are about 20,000 planetary nebulae in our galaxy at any given time. That might sound like a lot. But remember, the galaxy contains hundreds of billions of stars. Most of them won't create planetary nebulae. Red dwarfs, the most common stars, are too small. They'll just cool and fade. Blue giants are too massive. They'll explode as supernovae. Planetary nebulae are the fate of medium-sized stars, stars like the sun. And even then, they're brief, 20,000 years out of a 10 billion year lifespan. That's 0.02% of the star's life. A fleeting moment, a final breath, and then nothing. Let me tell you about the chemistry of planetary nebulae. They're incredibly complex. Spectroscopy, the study of light, broken into its component wavelengths, reveals dozens of elements. Not just hydrogen and helium, but carbon, nitrogen, oxygen, neon, sulfur, argon. Elements that didn't exist in the early universe. Elements that were forged in the cores of stars over billions of years. When we analyze the light from a planetary nebula, we're reading the star's biography. We can tell what kind of star it was, how massive, how old, what elements it created. It's like archaeology, but instead of digging through dirt, we're analyzing light. And the stories we uncover are breathtaking. Here's a question for you. Have you ever thought about what it means that the universe recycles itself? That nothing is ever truly lost? The sun will die, but the atoms that make up the sun won't disappear. They'll drift into space. They'll mix with interstellar clouds. And billions of years later, they will collapse into new stars, new planets, maybe new life. The carbon in the sun's core will become the carbon in some distant tree. The oxygen in its atmosphere will become the oxygen someone breathes. The iron in its depths will become the iron in someone's blood. Death in the cosmic sense is not an ending. It's a transformation, a passing on. The universe has been doing this for 13.8 billion years, and it will keep doing it for trillions more. Until the last stars fade, until the universe itself grows cold and dark. But that's so far in the future, it's almost meaningless to us now. For now, we have planetary nebulae, proof that even in death, stars can be beautiful, that endings can be gentle, that what we leave behind can glow. And when the sun finally sheds its outer layers, when it creates its own planetary nebula, it will be a monument, not to what it was, but to what it gave: light, warmth, life, and finally, in its last act, beauty. A gift to the cosmos, a reminder that even the most ordinary star in the right moment can shine in ways it never did before. But the nebula will fade, the gas will disperse, and what's left at the center of all that beauty is something small, dense, quiet, a stellar ember. The final remnant of everything the sun once was. Let's look at what becomes of that core. Take something the size of Earth and compress it until it weighs as much as the sun. Crush it down until a teaspoon of its material weighs 15 tons. Make it so dense that electrons can't move, can't orbit, can't behave like normal matter anymore. And then let it sit there, glowing. Not from fusion, not from burning, just from memory, from the leftover heat of what it used to be. This is a white dwarf, the final resting state of stars like our sun. Not dead, not exactly, but not alive either, just waiting, cooling, fading for trillions of years, longer than the universe has existed, longer than it will exist in any form we'd recognize. A white dwarf is patience made physical, silence made light. Here's what happens after the planetary nebula fades. After the sun has shed its outer layers, after the glowing gas has dispersed into space, what's left is the core. Just the core. A ball of carbon and oxygen about the size of Earth, compressed to unimaginable density. No fusion is happening. The temperature isn't high enough. The pressure isn't high enough. All the fuel is spent, but the core is still hot. Incredibly hot. Over 100,000 degrees Celsius at first, maybe more. And that heat radiates outward, slowly. The white dwarf glows. Not with the fierce brightness of a living star, but with a pale, steady light. Steady, white, hence the name. It's not a star anymore. It's an ember, the last remnant of a fire that burned for 10 billion years. Now let's talk about density. This is where things get strange. In a white dwarf, matter is packed so tightly that normal atomic structure breaks down. Normally, atoms are mostly empty space. The nucleus is tiny. The electrons orbit far away. But in a white dwarf, gravity crushes everything together. The electrons are pushed as close to the nuclei as quantum mechanics will allow. They can't get any closer. This creates something called electron degeneracy pressure. It's not a force in the traditional sense. It's a quantum effect. Electrons resist being in the same place at the same time. And that resistance, that quantum pushback, is what holds the white dwarf up. Not heat, not fusion. Just the unwillingness of electrons to overlap. It's bizarre, counterintuitive, but it's real. And it's what keeps white dwarfs from collapsing further. Let me give you a sense of what this density means. 1 cubic centimeter of white dwarf material, about the size of a sugar cube, weighs about 1 ton. 1 teaspoon weighs 15 tons. If you could somehow bring a chunk of white dwarf matter to Earth, it would fall through the ground, through the crust, through the mantle, straight to the core. Nothing could support it. And if it didn't vaporize from decompression first, it would just keep sinking until it hit something equally dense, which it wouldn't. Because nothing on Earth is that dense, not even close. This is matter at the edge of what's physically possible. 1 step further, and it becomes a neutron star. 1 step beyond that, a black hole. But white dwarfs sit right on that boundary, held up by quantum mechanics alone. In 1862, a telescope maker named Alvin Graham Clark was testing a new lens. He pointed it at Sirius, the brightest star in the night sky, and he noticed something odd, a faint point of light next to Sirius, a companion. Sirius B. At first, astronomers thought it was just a dim star, but when they measured its mass, they were shocked. It was almost as massive as the sun, but much, much fainter. How could something so massive be so dim? The only explanation was that it was incredibly small and incredibly dense. Sirius B was the first white dwarf ever discovered, and it completely upended our understanding of stellar evolution. Before that, astronomers didn't know stars could become so dense. They didn't know quantum mechanics would step in to prevent collapse. Sirius B was a revelation, a glimpse into the future of our own sun. Here's something that surprises people. White dwarfs don't stay white, not forever. When they first form, they're white hot. Over 100,000 degrees, they glow with a harsh blue-white light. But they're not generating any new heat. They're just radiating away what's left. And as they cool, their color changes. White dwarfs become yellow dwarfs, then red dwarfs. And eventually, after trillions of years, they'll cool down completely. They'll stop glowing. They'll become black dwarfs, invisible, inert, cold. But here's the thing. The universe isn't old enough yet for any black dwarfs to exist. The universe is 13.8 billion years old. The oldest white dwarfs are maybe 10 or 11 billion years old. And they're still glowing, still warm. It will take hundreds of billions of years for them to cool completely, maybe trillions. By that time, the universe will be a very different place. All the stars will have died. Galaxies will have drifted apart. The cosmos will be dark and cold and empty. And the only light will come from the last few white dwarfs glowing faintly, slowly fading into nothing. Now, let's talk about how white dwarfs cool. It's not like cooling a cup of coffee. A white dwarf has no atmosphere to speak of, no convection, no wind, just radiation. Heat escapes as photons streaming away into space. And because the white dwarf is so dense, so massive, it holds on to its heat for a very long time. Scientists have calculated the cooling curve, how temperature drops over time. At first, it cools relatively quickly, thousands of degrees over the first billion years. But then it slows. After 10 billion years, a white dwarf might still be several thousand degrees. After 100 billion years, it might be a few hundred degrees. And after a trillion years, it will finally approach absolute zero. But it will never quite reach it. Not exactly. There will always be a tiny bit of residual heat, a memory of the star it once was. Here's a question for you. What do white dwarfs look like up close? We can't visit one, of course, but we can imagine. The surface would be smooth, featureless, no storms, no spots, no flares, just a perfect sphere of crystallized carbon and oxygen wrapped in a thin layer of hydrogen or helium. The gravity would be crushing, about 350,000 times stronger than Earth's gravity. If you could stand on the surface, which you couldn't, you'd weigh hundreds of thousands of tons. Your body would flatten instantly. But the view would be worth it if you could survive. The sky would be black. Stars would shine without twinkling because there's no atmosphere to distort their light. And if you look down, you'd see the surface glowing faintly. Not bright, not dazzling, just a dull, steady luminescence. The last remnant of fusion that ended billions of years ago. In recent years, astronomers have discovered something astonishing. Some white dwarfs aren't just carbon and oxygen. They're crystallized, solid, like diamond. As a white dwarf cools, the carbon atoms in its core arrange themselves into a lattice structure, a crystal. The entire core becomes a giant Earth-sized diamond glowing in the dark. This isn't speculation. It's prediction based on physics. And in 2019, scientists found observational evidence. They studied the cooling rates of white dwarfs and found a population that was cooling more slowly than expected. The best explanation: crystallization. As the core solidifies, it releases latent heat, which slows the cooling process. These white dwarfs are transitioning from liquid to solid, from plasma to crystal. Over billions of years, they're turning into diamonds. The universe is full of them. Trillions of diamond stars scattered through the galaxy, invisible to us, waiting quietly in the dark. Now, here's something that people get wrong. They think white dwarfs are dead, finished, inert. But that's not quite true. White dwarfs can still do things, dramatic things. If a white dwarf has a companion star, something close enough to pull material from it can accrete matter. Gas from the companion spirals down onto the white dwarf's surface, building up in a thin layer. And when that layer reaches a critical mass, it ignites. Nuclear fusion starts again, not in the core, but on the surface. And the white dwarf explodes. Not completely, just the surface layer. A sudden, brilliant flash of light. This is called a nova. Novae happen all the time in the galaxy, dozens per year. They're caused by white dwarfs stealing matter and then erupting. And if the white dwarf accumulates enough mass, if it crosses a certain threshold called the Chandrasekhar limit, about 1.4 solar masses, something even more dramatic happens. The entire white dwarf detonates, a type Ia supernova, one of the brightest explosions in the universe. For a few weeks, a single white dwarf can outshine an entire galaxy. Our sun won't do this. It doesn't have a companion close enough. But other white dwarfs will. And when they do, they briefly reclaim their place as stars, bright, powerful, unforgettable. Let me tell you about one more white dwarf, PSR B1620s 26b. It's not famous, it's not nearby, but it's ancient, incredibly ancient. This white dwarf is part of a triple systems in the globular cluster M4, about 12,400 light-years away. The system includes a pulsar, a white dwarf, and a planet. The planet is 12.7 billion years old, almost as old as the universe itself, and it orbits both the pulsar and the white dwarf. This planet survived the red giant phase of its original star. It watched its sun swell and die. It watched the planetary nebula form and fade. And now it orbits a white dwarf and a pulsar, two stellar corpses in eternal silence. That planet is proof that some things survive, that not everything is destroyed, that even in the death of stars, remnants persist, orbiting, waiting, remembering. Here's the thing about white dwarfs. They don't forget. Not really. They carry the memory of their past in their composition, in their temperature, in their slow, inevitable cooling. A white dwarf is a biography written in physics. If you could analyze it closely enough, you could tell what kind of star it used to be, how massive, how long it lived, what elements it created. You could reconstruct its entire life from what's left. And in that sense, white dwarfs are not just remnants, they're monuments, testaments, proof that something was here, something burned, something shone. And even though the burning has stopped, even though the shining has dimmed, the memory remains, encoded in carbon and oxygen, locked in crystal, cooling, fading, but never quite gone. Our sun will become one of these. Billions of years from now, after it sheds its outer layers, after the planetary nebula fades, all that will remain is a white dwarf, about the size of Earth, glowing faintly, cooling slowly, alone, and it will sit there for trillions of years, longer than we can imagine, longer than anything we know will last, just glowing, just remembering, a faint echo of the star that once warmed a living world. But before we get there, before the sun becomes a white dwarf, something else happens, something closer to home, something more immediate, because the sun's transformation won't just affect the sun, it will affect everything around it, the planets, the moons, and especially Earth. Let's see what becomes of our world when the sun begins to fade. Picture Earth, not as it is now, blue, green, alive, but as it will be. Red skies glowing with the light of a dying star. Oceans turn to vapor, continents cracked and molten. No trees, no birds, no breath of wind, just heat, silence, and the slow, inevitable erasure of everything that ever mattered to us. This is not science fiction. This is prediction, based on physics, based on observation, based on what we know happens to planets when their stars begin to die. Earth will not last forever. It cannot. And long before the sun becomes a white dwarf, long before it sheds its outer layers, Earth will have already become uninhabitable, lifeless, a burnt monument to what once was. The timeline starts sooner than you might think. We have about 1 billion years, maybe less. Not until the sun dies, but until Earth becomes uninhabitable. Here's why. The sun is getting brighter, slowly, imperceptibly, but measurably. Every 100 million years, the sun's luminosity increases by about 1%. That might not sound like much, but it adds up. In 1 billion years, the sun will be about 10% brighter than it is now. And that 10% is catastrophic. Earth's climate is delicately balanced. A small change in solar output has massive consequences. As the sun brightens, Earth's surface temperature will rise. Not by a degree or two, by tens of degrees. The oceans will start to evaporate. Water vapor will fill the atmosphere. And because water vapor is a greenhouse gas, it will trap even more heat. A runaway greenhouse effect. The same thing that happened to Venus billions of years ago. Let me walk you through it. Right now, Earth's average temperature is about 15 degrees Celsius. Comfortable, livable. But in 500 million years, the temperature could rise to 30 degrees. Still survivable. Uncomfortable, but survivable. In 800 million years, it might reach 50 degrees. Too hot for most plants. Too hot for most animals. Ecosystems will collapse. Forests will die. Deserts will expand. The equator will become uninhabitable. Life will retreat to the poles. And then, in about 1 billion years, the temperature will exceed 100 degrees Celsius. The boiling point of water. The oceans will evaporate completely. The atmosphere will become a thick, choking blanket of steam. And Earth will look like Venus. A hellish, lifeless world shrouded in clouds, baking under the relentless heat of a brightening sun. Here's something most people don't realize. The end of life on Earth won't be dramatic. No asteroid impact. No supernova. Just slow heating. Gradual change. One species after another going extinct. First the coral reefs, then the rainforests, then the crops, then the insects, then the mammals, one by one, until nothing is left. Scientists have tried to model this, to predict when the last living thing will die. Some estimates say 800 million years, some say 1 billion, some say 1.5 billion. It depends on the specifics, how fast the sun brightens, how resilient life is. But the outcome is the same. Eventually, Earth will be too hot, too dry, too poisoned by its own atmosphere. And life, all life, will end. Not with a bang, but with a slow, suffocating whimper. Now, let's fast forward. 3.5 billion years from now. The sun is nearing the end of its main sequence phase. It's much brighter now, maybe 40% brighter than today. Earth's surface is molten. The atmosphere has been stripped away by solar wind. The oceans are long gone, boiled off into space. What's left is a barren rock glowing red hot, tidally locked to the sun. One side always facing the star, one side always facing away. Eternal day, eternal night. And then the sun begins its red giant phase. It swells, grows. The sky, if there were anyone to see it, would fill with red light. The sun would stretch from horizon to horizon, and Earth, still clinging to its orbit, would feel the heat intensify. 1,000 degrees, 2,000 degrees, 3,000 degrees, the surface would melt, vaporize. Atoms would be stripped away by the solar wind. And eventually, maybe Earth would be swallowed whole. But here's where it gets uncertain. Scientists aren't sure if Earth will be consumed. The sun will lose mass as it becomes a red giant. About 30% of its mass will be blown away into space. And as the sun loses mass, its gravitational pull weakens, which means the planet's orbits will shift outward. Earth might drift far enough to escape, or it might not. The calculations are close, too close to call with confidence. Some models say Earth survives, others say it's engulfed. But even if Earth survives, it won't be Earth anymore. It will be a charred, airless husk, a cinder, a ghost of a world that once teemed with life. In 2020, astronomers made a discovery that gave us hope, or maybe just curiosity. They found a planet orbiting a white dwarf. The planet, called WD 1856b, is about the size of Jupiter, and it's orbiting incredibly close to the white dwarf, closer than Mercury orbits the sun. This shouldn't be possible. When the star became a red giant, it should have swallowed the planet. But somehow, the planet survived. Maybe it was farther out and migrated inward later. Maybe it formed after the star died from leftover debris. We don't know, but it proves that planets can survive their star's red giant phase, not intact, not unscathed, but they can survive. And if a giant planet can survive, maybe a rocky planet can too. Maybe Earth will cling on, battered, scorched, but still there, orbiting a white dwarf in eternal twilight. Here's a thought experiment. Imagine humanity still exists a billion years from now. Unlikely, I know, but imagine. What would we do? We couldn't stay on Earth. We'd have to leave, migrate to the outer solar system, maybe Mars, maybe the moons of Jupiter or Saturn, Europa, Titan, worlds that are frozen now but might become habitable as the sun brightens. Or maybe we'd leave the solar system entirely, build generation ships, travel to another star, find another Earth, another sun, start over. It sounds like science fiction, but it's the only option. Stay and we die. Leave and we might survive. Humanity's fate in the distant future will depend on whether we can let go of the world that made us, whether we can say goodbye to the only home we've ever known. But let's be honest, humanity probably won't be around that long. A billion years is an unimaginable span of time. Homo sapiens have only existed for 300,000 years. Civilization, only 10,000 years. In a billion years, if we survive, we'll have evolved into something unrecognizable, or we'll have gone extinct long before, from climate change, from war, from asteroid impacts, from diseases, from any of 1,000 disasters that could wipe us out in the next few centuries. The sun's death is a distant concern, a far future problem, but it's real, and it's inevitable. And it reminds us that everything ends, not just individuals, not just species, but worlds, planets, solar systems, everything. Now let's talk about what happens to the other planets. Mercury will definitely be consumed. It's too close. When the sun swells, Mercury will be the first to go. Vaporized, absorbed, gone, Venus too. Both inner planets will vanish into the sun's outer envelope. Mars might survive. It's farther out. And as the sun loses mass, Mars's orbit will expand. It might drift far enough to stay safe, but it will still be scorched. Any atmosphere it has will be stripped away. Any ice will sublimate. Mars will become even more barren than it is now. And the outer planets, Jupiter, Saturn, Uranus, Neptune, they'll be fine, relatively. They're far enough away that the sun's expansion won't reach them, but they'll change. As the sun brightens, their icy moons will melt. Europa's subsurface ocean will warm. Titan's methane lakes will evaporate. For a brief period, maybe a few 100 million years, these moons might become habitable. Liquid water, moderate temperatures, who knows? Maybe life will emerge there, or maybe we'll migrate there. A second chance, a new beginning. And then the sun will shed its outer layers, the warmth will fade, and the moons will freeze again. Forever. Here's something that breaks my heart a little. Earth has been home to life for 3.8 billion years. Bacteria, algae, fish, dinosaurs, mammals, birds, trees, flowers, humans. Billions of species over billions of years. All of it nurtured by the sun. All of it made possible by the delicate balance between Earth's distance and the sun's output. And in a billion years, all of that will be gone, erased. Every fossil, every bone, every artifact, every trace of civilization, melted, vaporized, scattered, as if we never existed. Future alien astronomers, if they visit our solar system, won't find any evidence of life, just a dead rock orbiting a white dwarf. They won't know that this planet once had oceans, forests, cities, dreams. They won't know we were here, and that's the truth of it. In the cosmic scale, we're invisible, temporary, forgotten almost as soon as we're gone. But maybe that's okay. Maybe it's even beautiful in a way. To know that everything is temporary, that nothing lasts, not mountains, not oceans, not planets, not stars. It makes the present moment more precious, doesn't it? The fact that you're here, now, breathing, thinking, feeling. That's not guaranteed. It's not eternal. It's a gift, a brief flicker of consciousness in an uncaring universe. And when it ends, when the sun finally dies and takes Earth with it, it won't be a tragedy. It will just be the way things are, the way they've always been. The universe creates, the universe destroys, and it moves on. Without sentiment, without regret, just physics, just time, just the slow unfolding of inevitable change. In the end, Earth's story is the story of every world, born from chaos, nurtured by a star, home to life maybe for a brief span, and then returned to dust, to gas, to the raw materials that will one day form something new, another star, another planet, another chance. The universe doesn't mourn, but we do. And maybe that's what makes us different. Not that we exist, but that we care. That we look up at the sky and feel something. Awe, fear, wonder, love. That we tell stories about stars. That we imagine futures and remember pasts. That we try to understand even when understanding changes nothing. So, what does all of this mean? What's the point of knowing the sun will die, of knowing Earth won't last? Maybe there isn't a point. Maybe it's just information, cold, distant, irrelevant to your daily life. Or maybe it's a reminder that time is limited, that change is inevitable, that the things we take for granted, the sun rising every morning, the air we breathe, the ground beneath our feet, are all temporary. And that if we want to survive, if we want to leave something behind, we have to act. We have to care. We have to look beyond ourselves, beyond our lifetimes, beyond even our species, to something bigger, something longer, something worth preserving even if we'll never see the result. But we're not done yet. There's one more thing to consider, one final thought to leave you with. Because the sun's death, Earth's end, they're not just facts. They're part of a larger pattern, a cosmic rhythm, the universe's way of renewing itself, of letting go. And in that letting go, there's something profound, something worth sitting with for a moment. Let's end where we began, in the quiet, in the stillness, in the understanding that even stars, even the brightest things we know must fade. And maybe that's not sad. Maybe it's just the way light works. We've come a long way together. From the birth of the sun 4.6 billion years ago, from a cold cloud collapsing in the dark to its distant future as a white dwarf cooling alone in the emptiness of space. We've watched it burn. We've seen it swell. We've witnessed the slow, inevitable transformation of a star that gave us everything: light, warmth, time, life itself. And now, as we reach the end of this journey, I want to leave you with something. Not just facts, not just timelines, but a thought, a feeling, something to carry with you when you look up at the sky and see that familiar yellow glow. Because the sun's story is not just about physics, it's about impermanence, about cycles, about the way the universe creates and destroys with equal grace, and about what it means to be a small temporary thing in a cosmos that doesn't care whether you exist or not, but somehow made you anyway. Let's recap the journey just for a moment. The sun began as nothing, a cloud of hydrogen and helium remnants of stars that died before it was born. Gravity pulled that cloud together, compressed it, heated it, and when the core reached 10 million degrees, fusion ignited. Hydrogen became helium, mass became energy, and the sun began to shine. For 4.6 billion years, it has burned steadily, reliably, boringly. And in that boring, steady burning, it created the conditions for something extraordinary. A planet at just the right distance. With liquid water, with a stable climate, with time. Enough time for chemistry to become biology, for single cells to become complex organisms, for fish to crawl onto land, for dinosaurs to rule and fall, for mammals to rise, for primates to look up at the stars and wonder why, for you to be here listening to this, thinking about a star. In about 1 billion years, the sun will brighten enough to make Earth uninhabitable. The oceans will boil, the atmosphere will thicken, life will end, not suddenly, but gradually, species by species, until nothing remains. And then about 5 billion years from now, the hydrogen in the sun's core will run out. Fusion will stop. The core will collapse, and the outer layers will expand. The sun will become a red giant, swollen, red, dying. It will consume Mercury, Venus, possibly Earth, and for a few 100 million years it will pulsate, swelling and contracting, fusing helium in its core, creating carbon and oxygen. And then it will shed its outer layers. A planetary nebula will form, glowing, beautiful, brief. And at the center, all that will remain is a white dwarf, Earth-sized, dense beyond comprehension, cooling slowly, glowing faintly, remembering. For trillions of years, it will sit there, alone, silent, fading, until the universe itself grows cold, until the last light goes out, until even memory fades. Here's what strikes me most about this story. The sun doesn't know it's dying. It doesn't know it ever lived. It's just following the laws of physics, gravity, fusion, thermodynamics. There's no intention, no purpose, no meaning beyond what we give it. And yet, in that mindless process, it created us. It created everything we know. Every sunrise you've ever seen, every warm afternoon, every shadow, every ray of light filtering through leaves, every photon that touched your skin and made you feel alive, all of it the product of hydrogen fusing in a core 93 million miles away. The sun gave us life without knowing, and it will take it away without caring. That's not cruel, that's just the way it is. The universe operates on scales so vast, so indifferent, that our existence barely registers. We're not even a footnote. We're a momentary fluctuation, a brief spark in an otherwise dark cosmos. And yet, here we are, conscious, aware, thinking, feeling, wondering. I think that's the real miracle. Not that the sun exists, but that it exists in such a way that we can think about it, that we can measure it, model it, predict its future, that we can feel sad about its death, even though it won't happen for billions of years, that we can look at a star and see not just light, but a story, a beginning, a middle, an end. The sun is matter, but we make it meaning. And maybe that's what consciousness is for, not to survive, not to reproduce, but to bear witness, to look at the universe and say, I see you, I understand you, I know you won't last, and neither will I. But for this brief moment, we exist together, and that's enough. Carl Sagan once said, "We are a way for the cosmos to know itself." I think about that a lot. We're made of atoms forged in stars, the iron in our blood, the calcium in our bones, the oxygen we breathe. All of it came from stellar nucleosynthesis, from stars that lived and died billions of years ago. We are quite literally stardust, animated stardust. Stardust that can think, that can wonder, that can look back at the stars and recognize its origins. And when we die, when the sun dies, when everything ends, those atoms will return to space. They'll drift, they'll mix with clouds of gas, and eventually they'll become part of something new, another star, another planet, maybe another form of life. The universe recycles endlessly. Nothing is ever truly lost, just transformed, rearranged, given a new shape, a new story. Here's something I want you to remember. The sun has been the most important thing in human history. Every civilization that has ever existed looked up and saw the sun. They worshipped it, feared it, thanked it, built temples to honor it, told stories about it. The Egyptians called it Ra. The Greeks called it Helios. The Aztecs believed it needed blood to keep burning. The Inca called it Inti and built an empire around it. And even now, in our scientific age, when we understand fusion and photons and hydrogen, the sun still holds power over us. We still plan our days around it. We still seek it out. We still turn our faces toward the light. Because on some deep instinctual level, we know the truth. The sun is life. Without it, we are nothing. And even knowing it will die, even knowing we won't be here to see it, we still feel something when we think about it. Gratitude, maybe, or reverence, or just the quiet acknowledgement that we were lucky. Lucky to be born on a planet orbiting a stable star. Lucky to have had time. Lucky to have been here at all. I wonder what future beings, if any exist, will think when they look at our solar system billions of years from now. They'll see a white dwarf, faint, cooling, maybe a few rocky remnants orbiting it, charred planets, lifeless moons. No trace of what was here, no trace of oceans or forests or cities, no evidence that anything ever lived. They won't know about us. They won't know about Earth. They won't know that for a brief period measured in billions of years, but still brief on the cosmic scale, this system was special. That it had life, that it had consciousness, that it had beings who looked up at their star and loved it. And maybe that's okay. Maybe we don't need to be remembered. Maybe it's enough to have been here, to have existed, to have mattered if only to ourselves for a little while. But here's the thing. Even though the sun will die, even though Earth won't last, even though everything ends, the story doesn't stop. Because the atoms the sun creates, the carbon and oxygen forged in its final breaths, will spread through the galaxy. They'll become part of new stars, new worlds, new possibilities. The sun's death is not an ending. It's a passing on, a gift to the future. The universe has been doing this for 13.8 billion years. Stars are born. They live. They die. They create heavier elements. Those elements form new stars. And the cycle continues. Each generation of stars enriching the cosmos, making it more complex, more interesting, more capable of producing things like planets, like life, like us. We are the product of countless stellar deaths. And when our sun dies, it will contribute to the next generation. The cycle will continue, long after we're gone, long after everything we know is gone. The universe will keep creating, keep destroying, keep moving forward, indifferent, eternal, beautiful. So, what do we do with this knowledge? How do we live knowing that everything is temporary? Knowing that the sun will die, that Earth will end. That we individually and as a species are fleeting, I think we live fully, presently, gratefully. We appreciate the sunrise, the warmth on our skin, the light filtering through trees. We recognize that these things are gifts, unearned, undeserved, just the product of physics and luck and billions of years of cosmic evolution. We take care of the world we have, not because it will last forever, but because it's ours. Now, and that's enough. We create, we love, we wonder, we tell stories, we look up at the sky and feel something. And when our time is over, when the sun's time is over, we let go. Because that's what the universe does. It creates, it lets go, it moves on. And there's a kind of peace in that, a kind of acceptance. Nothing lasts, not even stars, not even the things that seem eternal. But while they're here, they shine, and that's all we can ask for. Do you feel it? That strange mix of sadness and wonder. Knowing the sun will die, but also knowing it gave us everything. That's the human experience in a nutshell. We're caught between impermanence and meaning, between the vastness of the cosmos and the intimacy of our own lives. We know we're small. We know we're temporary, but we care anyway. We love anyway. We create anyway. And maybe that's the most defiant, most beautiful thing we do. Not that we survive, but that we care even when caring doesn't change the outcome. Even when the universe doesn't care back. We care, and that matters, at least to us, at least for now. Thank you for being here, for listening, for drifting through this long, quiet story about a star. I know it's not easy to think about endings, about death on a cosmic scale, but I hope in some small way it brings you peace, or curiosity, or maybe just a deeper appreciation for the present moment, for the warmth you feel when you step outside, for the light that touches your face every single day, for the fact that you're here at all, on a small planet, orbiting an average star, in an ordinary galaxy. And yet somehow, you're thinking, you're feeling, you're wondering. And that's extraordinary. That's the real miracle. Not that stars exist, but that we can know them, understand them, mourn them, love them. The sun will shine for billions of years yet, long after we're gone, long after everything we know has turned to dust. But right now in this moment, it's shining for you. And maybe that's all that matters, not what comes after, but what is, now, here, the light, the warmth, the quiet companionship of a star that has been with us from the very beginning, and will be with us in some form until the very end. Sleep well, dream gently, and when you wake, step outside and feel the sun on your skin, not as a scientific object, not as a ball of plasma, but as a friend, a companion, a gift, because that's what it is, a gift, and it won't last forever. But then again, neither will you, and that's what makes it beautiful. Thank you for listening, thank you for caring, and if you'd like more of these quiet journeys through science and space, more stories told softly in the night, I hope you'll return. There are so many more stars to explore, so many more wonders waiting in the dark. Until then, rest easy. The universe is vast, but for now, you're here, and the sun is shining, and that's enough. Good night.